I would like to introduce our closing plenary, the keynoter, Jeandrew Brink. The title of what her keynote will be is Noble Queries Regarding the Nature of Space-Time. And the lady who will present this is Jeandrew Brink. You will have met her around here. She's a great lady to speak to. Essentially, well, she's going to talk about many things. One of the key things she will be talking about is this, GW 170817. That stands for gee whiz, which is an exclamation of awe and surprise. And there's the serial number, starting with number 1 with Galileo. If you believe that, you'll believe anything. That stands for gravity wave, and the date 2017, August the 17th. And she will talk about that in great details. I'm not going to do that at all. I would like to make a few comments from the scientific or the science publishing perspective. It turns out that on the same day that the observation was made, 100 preprints were registered to start talking about this. 100 on the same day. The definitive reference, as I have it, is a certain Mr. Abbott, multi-messenger observations of a binary neutron star merger. 1 to 59 pages. The interesting thing is that page 36 to 59 was devoted to just the name of all the authors and the institutions they worked for. There were 4,000 co-authors, which is a large number. People that know more about this than I do say that's about 1/3 of the total population of astronomers worldwide. And they came from something like 953 different institutions, observatories, universities, and stuff like that, which is astounding. I would like to show you what Scientific American said about this in May 2018. And just like that, with his observation, several of astronomy's unsolved problems dropped like swatted flies. But they say, but as always, it brought up many new questions as well. And that, of course, is the history of science. As we learn more, new issues and new problems arise. Jeandrew has been awarded a PhD in theoretical physics from Cornell University on the pulsation of neutron stars. She won the Sherman Fairchild Prize postdoctoral fellowship at Caltech with a guy called Kip Thorne. He's the guy who won last year's physics prize, the Nobel Prize. There she spent 5 years working on numerical relativity, testing Einstein's theory of general relativity and gravitational wave modeling. If you get a gravitational wave, what on earth does that mean? Kip Thorne was awarded last year's Nobel Prize in physics with 2 colleagues. She returned to South Africa in 2010, continues working on testing general relativity using pulsar timing and gravitational wave detection. She'll talk about that. She serves on the International Pulsar Timing Array Steering Committee. She's very eager to facilitate South African research in pulsar timing and gravitational wave physics. Ladies and gentlemen, please welcome Jeandrew Brink.
Okay, can you hear me? Yes, I usually say that in honor of Stephen Hawking, which is how I opened every talk. And thank you very much for the invitation to come and talk at INCOSE again. It's always a pleasure. I think you have the most, you're a connoisseur of eclectic speakers, and I've learned a lot from this conference, from the people. I commend you on your dedication to actually starting young scientists. Your programs with Jason Moy and the problems you choose are wonderful. So my field, since I spoke to you last, has exploded. It has been a wonderful 2 years for gravitational wave astronomy. The image you see over here is related to that GW 170817. As Ed mentioned, it is the most observed event in astronomy to date. It has pulled together communities in almost every country that has telescopes, and almost every wavelength, and the things we have learned is tremendous. Just a few things off the bat that I didn't even think about. It's the largest producer of platinum. So or platinum elements in the world. Platinum and gold is one of the main projects of this collision. Just to introduce the pictures that you see on the left, I need a pointer. Do I have one? Okay, so on the left, there's the gravitational wave density, and on the right, there's the electromagnetic magnitude of the waves that are emitted. And I'll go into greater, this is a simulation, but I'll go into greater detail of the actual observations that we've had towards the end of the talk. Before I go on, though, I have to admit that your conference's name has had me amused. I also have to admit that I'm a bit of a connoisseur of the Stone Age. I really like rocks, be it rock climbing with space age technology or just simply stone construction methods that they've used through the ages, in particular dry stone construction methods. And here's one local example. It's Lesotho. I visited there about a few weeks ago to look at the Lesotho Highlands water scheme, and I was fascinated by the construction they have. So, and then the second part, human innovation, I don't view the Stone Age as not having had innovation. And I appreciate the innovation that was there, but a lot has changed, and I often ask the question of, in the South African context, where we sort of often have the digital Stone Age overlapping, can we set a course that is optimal? Okay, so another picture from my visit from the Poliali Dam site. Next year, this will no longer be so. In 2026, when the engineering site or project is completed and you're getting your water from here, there will be a massive dam wall sitting over there. So there is a cost to innovation if you don't do it well. Sometimes you count the cost. But nonetheless, this picture made me think of a quote that I like, and since there have been a number of poets in the audience so far, this one in particular is nice with respect to my field. It says, "It may be strange, but who would change time's course to slower speeding?" And it was written long before we had the theory of general relativity. In fact, the concept that time could be changed didn't even exist. And now we know how to do it. We just put a very large black hole near whatever place we want to change the time. And in fact, we implicitly use this knowledge whenever we do calculations with the GPS, because the Earth, in fact, does do that. So it's a very practical thing. Another interesting vignette with my field is that first religious people, then philosophers, and finally relativists. The physicists were the last ones to actually realize that time was relative. So anyway, enough philosophy for a while. So I've made a list of innovation drivers. As it's no formal list, it's what I've collected as I've thought about things. And mainly within the context of revolutions within theoretical physics. Or not theoretical physics per se, our perception of the world. So it's conceptual shifts. Einstein's a great example of the person that did this. New technology, either the dam construction techniques, tunnel engineers, or laser and quantum mechanics, or sort of control over the quantum mechanical world that permitted LIGO to make its gravitational wave discoveries. Social organization, the way we structure research groups, the way we structure societies, the way we interact with governments. Communication and computing is a big one in the last few years. And then finally, enabling environments, funding stability and having a clear aim are things that are on the brink of failure and success. And if you have all of those things, then you win a Nobel Prize and tremendous insight, dedication, and a whole group of thousands of people. So I'm going to look more carefully at the pathway to the Nobel Prize. So much has been said about this, so when I was preparing the talk, it was sort of what would I add to what was new, and what I thought of is the quirks and the interactions and the discussions that are behind the scenes I would try and convey, rather than a full catalogue of the science and the thoughts and the technology that was developed to do that. Having said that, please do go and look at the Nobel Prize speeches. They were very well coordinated between these three men. They know each other very, very well. So just to introduce you, this is Ray Weiss. If you want to see him in color, the dude's there. Barry Barish and Kip Thorne. So Ray was the mind that designed this experiment. Okay? A lot of the technical and physical innovations of how you actually make an experiment that can measure the millionth the width of a hydrogen atom was due to Ray. Barry Barish was not a gravitational wave astronomer. He's basically the project manager, and if your community is sympathetic to the need of being able to manage this large group of people with completely different competing desires, aims, and things, and Barry Barish is very, very good at that. He not only got the initial funding, he got the various communities together, he started the LSC, which is LIGO Scientific Collaboration. So he actually made the link between the engineering project, the site, the science, and then the ultimate astronomy community, which was initially very, very opposed to building this instrument because they viewed it as a threat. In fact, it was initially funded through the physics program, not through the astronomy program, because there was so much opposition. And the person who helped barter this with these two, the Nobel Prize shared was a half year, a quarter year, and a quarter year. The person I know best is Kip Thorne. I spent 5 years in his research group. I have a tremendous amount of respect for him. In fact, I went back and visited this year, and I asked him, well, how's your life changed after winning the Nobel Prize? He says, no, not much. I just have to say no to more speaking engagement, but my secretary is suffering. So he's a very humble man. I gained a tremendous amount of insight from discussions with him, not just from the management and the oversight of the whole collaboration, but also from general relativity, which is a subject I love. So just the other pictures here, this is not an artist tradition, actually the real simulation, or if you managed to look at the source, okay, let me take one step back. This is the graph for which they won the Nobel Prize. It's basically you convince about 1,000 people to make you a squiggly graph like this, and they give you 7 million Swedish krona. But it was actually a lot more complicated than that. This is the physical observational data. The event that took place was the collision of two black holes and the release of about 3 solar masses of energy. Okay? And I'll say a little bit more about black holes in a moment. So what I'm going to do now is introduce a few of the concepts, and then I'm going to go on to the discovery of the physics. So I'm a reductionist, so I like to start from very basic first principles. If I divide physics, the knowledge of nature, into its small parts, you have the study of the very many, the very small, and the very big. And statistical physics and fluids sits up there. Quantum mechanics, which won this year's Nobel Prize, or the techniques associated with it, sits there. Gravitation sits over there. It comes from the Latin word gravitas, meaning weight. It's mostly attractive. It's a very, very weak force. And Einstein was instrumental in establishing those two roots. What basically happened is you split classical physics into the quantum world, the study of the very, very small, the gravitational world, the study of the very big, and he had problems with the interpretation of quantum mechanics for the rest of his life. Even though his discovery of the photoelectric effect started this, sort of helped start this field, he was never comfortable with it. And we're actually, ironically, we'll go back to Copenhagen. We had many of the discussions about quantum mechanics. Let's look at gravitation, and in your honor, I have put Galileo in there. So if you look at my list for things that resulted in innovation, there's your observational tools, the telescope with Tycho Brahe and Galileo. Sort of empirical knowledge, it went through its empirical stage where people simply looked at what was there and tried to make sense of it. You had a titan like Newton that started classical mechanics, invented calculus, and gave us a mechanistic, almost clockwork universe, okay, where everything, known the initial conditions, you know exactly how things evolve. Then you have Einstein, and he gave us general relativity. He coupled space and time. He expressed gravitation in terms of a metric. In fact, he changed the way we think about it from basically weight to a means of measuring, right? It became a theory of measurement in gravitation. He ironically did the same to quantum mechanics, even though he didn't like it, because quantum mechanics formulation is entirely on your observables and the way you measure. So even though he was reluctant to it, he changed the way we think into, and it's a natural way of describing physics. Simply, you describe the things you can measure. So both relativity and quantum mechanics are now theories of measurement. The future, we know there has to be a future, okay? These two are not the final formulation of nature because they're inconsistent in regions where they overlap, okay? And that I'll say about a little bit more. That's the stuff I'm really, really interested in, is probing those inconsistencies to see what goes beyond. Because there are things we cannot reconcile between the two theories. Right. Okay, so given general relativity, given the field equations that Einstein gave, he made predictions which cannot be found in Newtonian gravity. And I'm just going to summarize them, so when I start talking about the science, you know what I'm talking about. So the first one is there's a region of space, if you have enough matter concentrated there, from which nothing can escape. The name we give that is a black holes. And this is that image that I showed you a few slides earlier. It's simply that over at this point, there's a bunch of matter concentrated in a singularity, and light cannot escape in the region that has a radius of 2 mg over c squared. Okay? But what happens is the gravitational field is so strong there that not only can light not escape, that any light traveling around it physically bends around the black hole. So if you put your black holes in front of a stellar background, that's what it looks like. It bends the light shining from behind or from behind your back around the black hole, and that's actually by how you see it, not by seeing the black hole, but by its distortion. And that's why when two black holes collide, it's simply a geometric event, and it's very, very silent. The only emission you get is gravitational radiation. To the contrary, when you start having matter, it gets much more exciting, and that's why that event, GW 170817, was such a huge vindication for the field. Another fact was the solution to the field equation. So it's one thing to write down the theory for gravitation. It's an entirely different problem to solve those equations. It's not Newtonian mechanics where it's completely solved, and you know, if you have two bodies, it goes in an ellipse. It's much, much more complicated. I've spent a large time of my life doing that. But the easiest solution is the Schwarzschild solution. Irony is he found the solution while he was on the front lines in the Second World War, dodging bullets and actually physically in a trench. Sent it to Einstein, died 2 years later, but fortunately did. But nobody understood his solution. Its physical interpretation was found roughly 50 or 40 years later by Eddington Finkelstein, roughly at the same time where you started realizing you could form black holes and you could form neutron stars. So the mathematics was solved, the interpretation was not there. The rotating black hole was found by an Australian named Kerr a few years later, a very ruddy, robust kind of guy, but it's been immensely valuable. The closest one to us is Sagittarius A star. If you look up at the Milky Way at night, which is very nicely displayed from here, it's right there where the dust is. This, as I've already said, the magnitude of that excluded region is basically set by the event horizon, the region from which nothing can escape, and is dependent on the mass. Typically, astrophysical black holes have no charge, as opposed to no charge and no magnetic field, as opposed to neutron stars, which I'll come to next. And then there's another thing, like they call the uniqueness theorems, which is an anomaly. It basically says that any collapse that forms a black hole always looks the same. You know, so whether you've collapsed two neutron stars going together and formed a black hole, or whether you've had a big explosion and you formed a black hole. And it comes from the fact that gravity is so attractive that it simply pulls itself into either something spherical if there's no spin, or something spheroidal if there is spin. And that's an extremely strong prediction within general relativity, which we eventually test. Now, neutron stars, which was where that big event took place, and they become interesting because basically you're working at nuclear densities. So you basically have an object, say 1.4 times the mass of the sun, squashed into 10 kilometers. And the support is the neutron degeneracy pressure. So it's basically like a giant atom. That's a mischaracterization because we don't exactly know what the nuclear equation of state does in neutron stars, but it's a good first analogy. They're very warm. They have a surface temperature of 6,000 Kelvin, or 600,000 Kelvin. They have strong magnetic fields, and for some neutron stars that results in a radio beam propagating along the magnetic field lines. And it's one of the major sources of the SKA. Roughly 60% of our SKA time is being dedicated to following pulsars and making measurements with them. They are immensely valuable observational tools in astronomy. Okay, and they can rotate really, really fast, up to the fastest known pulsar that we can actually measure rotates 716 times a second. So you can imagine spinning the sun round roughly with the speed that my vocal cords are vibrating. It's something, it's quite a feat of nature. And there's just a caricature of the pulsar with its temperature and the magnetic field lines that are very strong. Okay, so that's sort of pure introduction. The next concept that Einstein's theory predicted was gravitational waves. And it was predicted very early on in 1918. And this is a simulation done of the actual first gravitational wave event that was seen and for which the Nobel Prize was initially awarded. This group that did the simulation is actually part of Kep's group, which I spent a lot of time with. It's several institutions you'll see at the end. And I mean, it's a huge programming team. I did some of the wave extraction stuff, which is shown at the bottom. So the simulation will play again. I'll just introduce it. At the bottom gives you an idea of the space-time, and it gives you an idea of the curvature. So it's pretty flat out over there, but here where the black holes are, it's extremely curved. And objects, if they were standing there, this is what the arrow indicates, they're actually dragged into motion to fall down the black hole. These objects are actually the event horizon, so those spheres that represent the mass. So, and I'll show it to you again. So these are the people that have participated, and that group kept started. The one more thing that you should watch at the bottom here is the amplitude of the gravitational waves. So initially when they're far out, it's roughly an ellipse that they're spiraling in. As they get closer together, the frequency increases. The frequency of the gravitational wave is roughly twice the orbital frequency of the object. And they get closer and closer and closer until they form what they call a common horizon, where the event horizon goes to both objects. And for black holes, that's the equivalent of forming one object and effectively merging. It's a very quiet event, although the maximum amount of power is put out just here at the merger event. And it slows down now. And once the black hole is formed, it's basically like an excited bell, and then it rings down with frequencies that are characteristic of gravitation, of the black hole mass and spin. So that's the only parameters that go in the end. And that also, once again, confirms the thing that I mentioned about the uniqueness theorems. Ultimately, it's simply the mass and spin that determines the final object. So this is theory. The simulation, initially when I was working on it, would have taken months to run. They've taken it down with a whole bunch of supercomputing tricks to days or hours, depending on number of processes you go on. So there's a tremendous team of people that do what they call source modeling. So this is actually solving these field equations in the strong field region. Okay, so let me move on to the experiment. These are the LIGO detectors. This is the physical realization of them, of Ray Weiss's dream. I'm actually not going to look at all the engineering advances that were taken to make it possible. They are continuing. I actually advise you to look at both mainly Ray's talk on the seismic isolation and things like that. But it's just, I want to get to the science, and it's a topic all on its own. There are beautiful mechanical as well as quantum mechanical advances that made the actual detection possible. The only thing that I should say is this distance is roughly 10 milliseconds, and it is this fact that the sort of relative alignment of the detectors as well as their separation makes it possible to point to where the source comes from in the sky. A rough idea is if the wave arrives at Hanford before Livingston, then the source is somewhere over there in the sky, and vice versa. So that's how the sky position is found. The only data we record is that wave, the chirp wave that you see and that you saw in the very first slide, as well as the bottom over here. From that data is where we get all our information from. Okay, so it's not a telescope. It simply has basically 2 photon points. This is Ray's original design, so I cut it off at the bottom here, but you can tell that he wrote down in the 1971 or 72, was almost entirely implemented. He was a genius when it came to conceptualizing something that was almost beyond reasonable technology at that point and demarcating how the development could take place. And it's an incredible credit to him that it is done. At the moment, so this, I don't know if this was in, at the moment the laser power to be able to measure these mirrors so accurately is extremely high. In fact, that was one of the fears and why they've systematically, ramped up the laser power, and we'll have an improved sort of measurement accuracy in the next science run simply because of the increased laser power. It's so strong that if it were to have deviated and there was an unexpected resonance, it would have seared the side of the beam tube, which would have been a big mess for the vacuum. But that's a completely different story. Okay, so what I am going to talk about is what actually was done with the data analysis. Because this is something, I mean, big science, where you work in these big collaborations, has changed the way we do science. The idea of the single tabletop experiment that does stuff for gravitational wave physics is not there. It just takes too many people. And then how do you deal with a scientific method? And what is less well known, you've heard all the blurb of gravitational waves being discovered. What you don't know is that it was challenged quite strongly by a group in Copenhagen. And how that interaction took place is something I'll tell you about. So the basic problem is simply noise. I mean, it's with the SKA, but the noise problem in LIGO was crucial. In fact, it was the reason why people said it was impossible, and it was also the reason why Kip and Barry Barish initially went to the US government and say, give us $1 billion, we're going to build you a machine that's going to measure nothing. And then if it works and it gives us the noise curve we predict, then you should give us another $1 billion, and then we'll actually see something. So they were very clever in sculpting their approach to the funding agency and very, very honest. But yeah, it's basically you want to find a whisper in a crowd of people, and that whisper has an amplitude of a fraction of the width of the hydrogen atom, and you tune your machine to find that whisper. That is the art of gravitational wave science. The fact that they achieved it 45 years ago, I mean, the target, like Ray's paper, was started 45 years ago, and it was shot into the future, and it bore fruit in 2015. So here it is. This is the actual noise curve from the first event. All these things can be downloaded from the LIGO site, and I'll add a list of very good links should anybody actually want to look at it or send students there, as well as a link to where I get all the videos. So it's entirely open. So this is the noise curve for this gravitational wave event. People were there's always this tension between proprietary data and keeping it so that you can get all the maximum science out, and making it available for inspection for the community. It was a public project, so that had to happen, and it had to happen before it became eligible for a Nobel Prize. But there was a lot of discussion on how much data you made available. And so what happened, and this bears for the discussion to come, they made roughly 32 seconds of data around the event that took place roughly over there. So this is the data stream for the Hanford detector, and for the Livingston detector, the event takes place roughly over there. Can you see it? Anybody? And no. And the reason is the noise or the signal is completely overshadowed. So this curve is actually taken away from the event by these, they call them violent string modes. So basically noise that is brought in by the suspension of the mirrors. Okay, as well as coupling to the electric grid and some of the vacuum pumps. Some of my friends that actually work on the experimental side know these things personally. So what they do when they analyze the data is they put in a filter, and how you apply it is also tricky, but they put in a filter that basically cuts out these bands and makes adjustment for the fact that the noise is not flat or not white. It's a whitening, but it's not a whitening. It's very important to say that. It's sort of properly done. And what they do when they apply that sort of filter to this, to the detector noise, is get the cleaned up signal. And the story of this discovery was, it was not yet in science mode, it was sort of in engineering mode. They were commissioning it for the first science run. And then when they saw this, they thought, no, somebody's put in an injection. Because the way the collaboration kept people from making a premature announcement is that there are a few people in the team that would put injections into the noise stream of which only they knew. So the postdoc, whoever was working and doing the observing, would never know whether it was a real signal they were analyzing as well, or injected one. It kept the collaboration honest. It also provided many ways of doing like the data analysis practice. And they had a number of practice runs, and people were terribly annoyed if they spent months literally preparing a paper and it turned out to be a fake thing. But it was necessary. It was the practice runs for this event which actually paid off tremendously because they all had all their papers prepared. So they looked at it and people started getting excited because, I mean, even though, yeah, it was strange, it was incredibly loud. And that was a blessing because it's very difficult to make a first discovery for a first detection for a blind search with a marginal sort of detection statistic. And this one isn't. It's a very loud event, and I'll show you the other events later on so that you can compare. So then the first thing you do is you check whether it's real, and a gravitational wave to be real has to be in at least both detectors. There are a number of other vetoes on the instruments. They have their weather, the electronics, like atmospheric electron cascades, solar, like they have this array of vetoes that they keep track of, and those channels are all publicly available as well now. But anyway, so the basic approach is you clean up the data, you then check that there's a coincidence between the two different detectors, and from the way you have to shift this data to do that immediately starts giving you an idea of where the source is located. And then what you go about is you go through and you do a matched filter. You basically look at the possible source catalog that you have, and you find the source or the template that matches the best. Okay, there are various ways of analyzing the data, and it is done in different ways. But the one that gets the highest statistics is this match filter search, and a number of people have had problems with that, and that has bearing on the next discussion. So basically, what they did was, for this first event, they made those 30 seconds public, or in fact, they made less than that public initially, and that was the only thing that was made public. The rest, all the discussions for the paper took place within the scientific collaboration. There was tremendous internal review. Of, say, 1,200 people. It's 108 institutions. So the example that I had mentioned earlier refers to both the gravitational wave and the radio, all the astronomers that you have. Okay, and then they claimed a direct detection of gravitational waves, and they thought that everybody would agree with them. And that's not what happened. Maybe I should do this first. Okay, so the gravitational waves are in the audible range. One way they actually look for them is whenever they have the monitoring scientists with earphones on, listening for chirps, because sometimes the ear can pick up things that we can't. You have also, the detector itself makes little glitches and chirps and stuff, and people have gotten to know them. They also have machine learning algorithms that try and take them out. But this is the typical sort of ramp up in frequency that occurs towards the end of the end spiral. Okay, and so it's tradition in gravitational wave physics to play these things. As I said, there was one event, the one I'll talk about later on, but a similar slew of papers took place when the first gravitational wave detection was made. It was a huge deal. It was a prediction 100 years old that had been measured for the first time, and it's very difficult to extract what is the essence of the ideas that are necessary from the slew of papers. And I like this quote by T.S. Eliot, and it's actually, ironically, the poem is called Choruses from the Rock. I have no idea why. But it is, where is the wisdom we have lost in knowledge, and where is the knowledge we have lost in information? And what happened after this discovery is there was a Kavli school, or a sort of a summer camp for scientists that have nothing better to do, held in Copenhagen, last year in June, and I'd made the mistake of writing a paper that said that if you observe a certain event with LIGO, you could test general relativity. LIGO is not the optimal instrument to test general relativity. LIGO was designed to observe gravitational waves. And that's a very important thing, because one of the massive slew of papers was testing general relativity with LIGO, and whenever I saw this, I was like, no, this is not going to happen. So anyway, I went to Copenhagen to try and convince them that this was not going to happen. But anyway, it didn't take much convincing. I'll give you the argument for why we can't yet test general relativity with LIGO. What else happened in Copenhagen was interesting, because there was a number of questions were raised about the actual discovery by a local group in Copenhagen. And what had happened, they'd approached the LSC previously, and they were sort of rebuffed. I mean, you have people that have been working incredibly hard. My friends, you can see them almost, you can see the toll that the discovery has taken on them, because there's a tremendous amount of calculations. And they said, no, we're right. And that's not the way science is done, because all the information was, except the few that data that I've shown, was behind the collaboration wall. And it brought forward a number of interesting questions with that even our first speaker, I think David Long, mentioned, right? So I just put it in your language, but basically, is the LIGO scientific collaboration the authoritative source of truth? Okay, in science, it doesn't work that. Science has to be verified. But if the experiment is entirely controlled by the people that have set it up, how does it work? And so it was very good that they released the data, but something else happened. The second question, sort of like large collaborative scientific method, and then trust. There's no reason that the discovery of gravitational waves should be taken on trust. It needs to be subjected to scrutiny from groups outside, and how to actually make that feasible, given the complexity of the experiment, was something that was spoken about. And then what happened was that there'd been another experiment that had claimed a gravitational wave discovery. And that experiment was a completely different experiment. It was called the BICEP2 experiment, which basically looked at the cosmic microwave background, looked at the magnetic field, and claimed to see an imprint of gravitational waves on the magnetic field. Now, just for the record, typically gravitational wave and magnetic spectrums or magnetic electromagnetic waves do not couple, except right near the beginning of time at the Big Bang, when the fields are extremely strong. And there's a prediction that the BICEP2 experiment claimed to have seen, and what had happened is they were wrong. They've been proved wrong by subsequent experiments, but the group that actually had, or the theoretical group that had been most vocal in opposing the result, was from Copenhagen. So they had confidence in killing gravitational wave results, legitimate confidence. They are very good at their data analysis. And they then took the data that had been made public, did a completely independent analysis, tremendously to their credit, and claimed to see residual noise, which put at risk the gravitational wave announcement. Okay? They first decided to discuss it quietly, and then they were sort of pushed away by the collaboration, and then the lead of the Copenhagen group then made some very provocative statements in public, basically claiming LIGO was wrong. And so, although I'm not part of the LIGO scientific collaboration, my friends that were actually conducting the discussion were there. And what had happened was that, and eventually when they got to the point of listening to each other, both groups were right. The data that had been released by the collaboration had been released as a tutorial, so not all the information of whitening the data had been given. They'd also not released enough data to actually get a good sort of null stream, or sort of to design that filter that takes out the violin modes without corrupting the actual signal. So the people that had done the reanalysis actually legitimately found that there might have been some residual thing, and there was some confusion, but they were both right. And this interaction, while it was initially frustrating for both teams, and resulted not only in the change at which the way that LIGO made the data public, and in fact an improvement, it resulted in other ways of looking at the data that was useful. And it just underscored once again that, in some sense, assaulting the data is always the authoritative source of truth in science, not necessarily the people, the process project in the collaboration. So it was a useful lesson, and it was fun to be part of. And the discussion took place. I mean, this is an old picture which I picked up simply because I like the history. I mean, the discussions took place in this room, so it was kind of nice for me to sit there too. And just hear a tribute to Einstein, where him and Bohr were discussing quantum mechanics and the nature of making measurements there. Him trying to always find, to say that God doesn't play dice, in some sense remove the probability part to quantum mechanics. Struggled that for the rest of his life. But anyway, it was ironic that one of the biggest results that verified his theory was assaulted again in the same way as he discussed with Niels Bohr at the Copenhagen Institute. The discussion was actually never totally resolved, as far as I know. What happened was fortuitous in that while it was taking place, it's quite interesting, I'm not behind the wall, the scientific collaboration wall, but I know the collaboration well enough to know that when my friends start not talking and responding to me, they must probably analyzing another gravitational waves event. And during the discussions with the testing GR, 2 of the events happened. 2 more events happened, one of which was that massively important one. Okay, so the Copenhagen groups sort of improved the way, or sort of made the discussion of looking at the data analysis richer. What stopped the discussion as to whether or not LIGO had seen a real thing was the truth. I mean, what happened is you saw this event, which, by looking at that waveform of the event, you could establish the masses of the objects that had collided, okay? And that indicated that they were neutron stars. Typically, neutron stars have a mass below 2 to 3 solar masses, and black holes have masses higher than that. So if your mass is lower than that, you suspect it was a neutron star, but an array of telescopes actually picked up the real deal. And I'm going to talk about that a little bit more towards the end of the talk, exactly what measurements were made. So they saw the EM observations, and that put pay to any reservation that the gravitational wave event was real, or that they'd been looking at some machine noise. You saw both. And they agreed beautifully. And it literally, the event that they saw in the optical is an artist's representation. Is it basically a giant fireball? They call it a kilonova. It is a massive collision, and it's also literally where most of our heavy elements are formed. Okay, so this is the signal that's been cleaned up, the sort of the chirp signal over there, and this is where it could be found in the sky, just from the gravitational wave measurement. What also happened for these 2 events, these are the 2 that happened just after each other. These last numbers are basically the date of when the event is recorded in the time series. So these 2 events, what happened, the reason why they are so localized, in other words, this is basically the potential place where the source could be on the sky, is that they added a 3rd detector. So the triangulation was now proper triangulation instead of just 2 points, which led to this redundancy on the sky. The reason why there was a slew of papers, here is a graph of the actual observatories and a count of the space telegraphs around the world that were involved in the observation of the neutron star collision. It's an amazing array of collaboration. I'm going to talk a little bit now about testing general relativity, mainly because that's the reason I went to Copenhagen, mainly because that's what I do and I love it. And I want to put it in context so that when you hear LIGO and testing relativity, you don't get overly excited, because it's not designed to do that. And I'll show you why it's not designed to do that. The LIGO experiment, up until before the LIGO experiment, what we knew about black hole population came from X-ray measurements. When 2 black holes collide, they sometimes give off a faint X-ray signal, mainly because of the matter around them is accelerated to high frequencies or high velocities. So that's what we know about the black hole population, but that's restricted mainly to black holes that are low mass. So LIGO gave us direct insight into not only the progenitor's mass, but also the final project, because all those things you can get from the waveform and by fitting the waveform to the data. So all this information is new, and rightfully people got incredibly excited and said, let's see if Einstein is the right theory. And the LIGO can't yet do that. They've tried. I mean, you can do the analysis, but it's unlikely to do it soon. This second event that took place with the 2 neutron stars collapsing or colliding is found over here. you could once again pick off the two masses from your waveform. The final state of what was formed when they collided is still unknown. It's one of the big mysteries. It has a mass that permits it actually to be a neutron star, but we don't know. It's on the borderline, and that's what makes it a fascinating long-term study, because it'll give us insight into how you form the most massive neutron stars. In fact, the most massive known neutron star is found over there. So all these others are known neutron stars. They were discovered mainly by pulsar timing measurements. Okay, so you can pick up, there's a population of neutron stars that you can see directly, and a population that are known from pulsar timing. And and you can see that all their masses are clustered, except for this one, below 2 solar masses. And the reason is that the neutron degeneracy pressure can only support that much mass before the star collapses and forms a singularity. Okay, so there are various ways of testing general relativity. The one I'm interested in is an orbital test, basically finding out, it's like a geodesy project or problem, sort of, you try and establish the structure of the black hole by watching a satellite moving around the black hole. But I'm going to be even more abstract to that. I'm going to make a caricature of the current LIGO analysis, and to illustrate the complexity of the calculation beyond what I've already shown you. And actually, at a recent discussion, and due to the poets in the audience, somebody asked me the earliest reference for the problem you're solving. And I thought about it, and it comes from, and it's kind of, I was amused when I found it because of something that had happened with one of my students. So the reference comes from Job, which, if you don't know, it's a treatise on suffering, right? This dude has lost everything. He's lost his oxen, his children, everything. And he's sitting bemoaning his fate, sort of asking God why this has happened to him. And eventually God pitches up, and it's the longest dialogue God ever gives in the Bible. And it's sort of like, instead of saying, this is why it happened to you, he gives the guy a whole bunch of questions, right? So you can imagine everything goes wrong. Instead of getting an explanation, you get this list of questions. So it's basically, where were you when I laid the foundation of my earth? Tell me, since you're so informed, who set its measurements? Am I to assume you know? Who stretched the boundary line over it? On what were its bases set? Who laid its cornerstone? Okay. It's amazing in some sense, because I view gravitation as a theory of measurements. So that part got right. It's also amusing because I once had a student trying to help me test GR, and I was trying to motivate him to solve this fundamental problem, and possibly I got too impatient than I was, and I asked him, what have you been doing? And it turned out, no, he's from Liberia, and his family was having trouble with Ebola. It was during the Ebola outbreak, and I was like, I've really put my foot in it, but now I can at least tell him that God does it the same way, like focus on your problem and solve it. But anyway, so it's a Stone Age reference for my problem, and a poetic one. Okay, so 3,000 years later, we're still seeking fundamental questions, and when we test GR, we are really going for the stuff underneath. We're going after Einstein's dream of reconciling the two theories of measurement that he started, basically quantum mechanics and general relativity. And the place where we tested is in black holes, which we can now have tremendous insight to. And the other place is in cosmology, the Big Bang. Okay? Those are the two places where these theories are not consistent, where we can potentially get an experimental handle on how to proceed. Our tools have changed tremendously, right? In fact, the last 2 Nobel Prizes sort of span the gravitational and the quantum world, and they're tools that overlap. I mean, the optics in LIGO are quantum. The measurements it makes is of waves that have their origin in huge cataclysmic events. How do we do it? This is a caricature, and it was presented at Copenhagen mainly to get the discussion going about how people were thinking about it and what is the minimum amount of information we need to know. So you want to get at the real beast, but you don't have the real beast. What we have is Einstein's theory, okay, which is a very good approximation of the real beast. It's the best we have. It has made tremendous predictive power that we have systematically assaulted with experiments over the last century. But even Einstein's theory, we cannot solve exactly. Okay, so that's the formulation in terms of the field equations. We need to find solutions to them. So one thing we do in a strong field is we have those huge numerical simulations which take days for a single simulation, and it loses some of the detail, but it still can potentially capture the beast to the extent that the numerical error, which in some of those simulations is not completely controlled. Then, because we can't do many simulations, we sample it sparsely. So we now have our numerically sparsely sampled beast. We smooth it a little bit because not all the simulations agree 100%. Then even keep storing that data is too complicated. So what LIGO has done is it has made a series of phenomenological waveforms. It's basically a parameterized fit to the waveforms we see, okay? And it's assured to have a certain accuracy. Once again, a little error. So that's what we actually use in the analysis, and that, when I showed you the waveform that had been fitted, is the phenomenological beast. Then we have the detected beast, okay? And our data points in LIGO are not that many to resolve all the details, but this is roughly it. You get a detected beast, and you can choose the way you detect it. You either use match filtering, in which you sort of have a guide for your eye, or you just use direct detection. Then we can say that's consistent up until, then it's a matter of, right, okay, I mean, that's a play on words because anybody that's involved in the LIGO analysis was completely exhausted afterwards, so it's a bit of a pain. But really, what actually sourced the thing that we detected? And can you tell it apart? And it becomes a statistical question, sort of, which theory actually have? So some of the problems in testing GR is Einstein's theory, I can argue from Achilles' heels perspective that it is the simplest four-dimensional theory that can give us everything we need to describe data so far. It's a geometric theory. It really is, in many ways, I don't know, mathematically you can say it's the simplest theory. There are alternatives, and there's a proliferation of alternatives, and which is why I gave you that quote about T.S. Eliot. It's very difficult. You can test a specific alternative and say the data looks more like a lion than a bear, but the point is you don't know how many bears there are. And so designing that, even the test becomes very, very difficult because you actually have to ask the question within a theory of measurement itself. And so I spend a lot of time doing that, how I'm not going to try and go into. But the basic thing that happens with a LIGO experiment, right, is there are certain numbers for any waveform that you can get. The first number will determine the mass. The most dominant parameter in most of the waveforms is the mass. The second dominant parameter is the spin. It's basically like all waveforms have a nose, all waveforms have eyes. The third parameter is the quadrupole moment. And once you can start measuring that with statistical significance, you can start thinking of conducting a test. And LIGO is nowhere near that. When it gets there, I'll start being more serious with respect to the orbital tests. Okay, so if somebody says they've tested general relativity with LIGO, be skeptical. They've either tested a theory that's way out anyway, or they've made a massive discovery, and it's one of the two. It's most likely the former. Okay, so here I said the first number you get are the masses, that I've already covered. The next number that you can get from these observations is the spins. And this is a really interesting one. Note, we are not testing general relativity here. What we are testing is the formation mechanism of how the object was formed within relativity. And why the spin is important is it's actually quite difficult to form two black holes orbiting each other. And there are a number of mechanisms that they've suggested. The most popular one, and the problem is, it's very difficult to get the black holes from way out there close together before they merge. So it's easy to form black holes far apart. It's much harder to form black holes within close radius of each other to merge. And so the main formation mechanism at the moment is basically this one. You have two massive stars that are formed from a collapse of dust. One sort of matures and enters its giant phase, and it transfers mass to the other one, and we see lots of stellar systems that do that. Then it collapses if it's massive enough, above like 5 to 10, well, above, say, 5 solar masses, it can collapse into a black hole. If it's less, then it often forms a neutron star, and the other star remains that. Eventually, that one matures, transfers mass onto this thing, until there's sort of this common envelope where there's mass surrounding both of them, and that common envelope phase is crucial because there's drag within that common envelope phase, and it provides the explanation of how the black holes get close enough to eventually merge with each other. The problem is, if this one becomes a black hole over there, they'll just stay out there because the emission when two black holes are far apart is minimal, right? It's the same reason the Earth doesn't spiral into the sun. Simply, if two black holes are far apart, the emission due to gravitational radiation simply is going to leave them on an ellipse for eternity. So when the thing that bears explanation when we see a merger event is how did the two get so close? And the explanation here is that you have this stage during the evolution at which the viscous drag of this common envelope actually shrunk the orbits a lot. And that theory you can test by determining the spins, because if you work this out for many, many samples, it actually has an imprint on the spins. And that is why people are so terribly interested in what the spins are. And this is the first, or possibly the most important thing you can get from direct gravitational wave experiment, or sort of measurements. Okay, so how much time do I have? 10. Okay, so I'm going to give you a quick run over of the neutron star event. For every gravitational wave event, they make a fact sheet for that event that took place. It is the longest event that we've seen. It is the false alarm rate. There's no chance that it's a false alarm rate. The total mass is 3.2 solar masses. And this is how they knew, and the two initial masses are below 2 solar masses. And this is how they knew, LIGO knew, that it was most likely a neutron star. And another interesting thing over here is the latency before they released it. I don't know if they say that here. Anyway, they took a couple of hours before they released the results and sent out the alert that it's a neutron star. And when it's a neutron star, they basically send the alert out to almost any optical, infrared, all telescopes available, because they've anticipated this event, and there have been sort of trial runs, even when they were doing the dummy simulations. Oh, this is the latency. This is the amount of time it took them to calculate where this event could potentially be. And because they had the 3 detectors, Virgo included, they got a much better localization than previously. And even before they had the localization, they took roughly, I think, 27 minutes before they alerted the other things that they knew they had a neutron star. And that's that for that graph. Okay, so this is a comparison of all the events known to date. This first one was a whomping loud one that was easy to see. This other one here is also very interesting. That one is too low for them actually to count it as an event. And then these other two were quite loud and easy to detect, but not really different from this one. This is the 1708-17. The reason it takes such a long time is because the masses are low, the gravitational wave emission is less, power is less. So the in-spiral, it stays for a longer time at a certain frequency. So it was in band for 60 seconds. This is the longest an event has ever been in band in LIGO. And we'll just wait until it makes its chirp. So for this event, the statistics, they needed to use match filtering because the statistic is built up over the whole event, right? Whereas that one was so loud, you could simply see the waveform after you'd filtered the noise. This one, you physically had to do the match filter. This is the thing that set the rest of the observational world into ecstasy. So that was the, sorry, I just have to do that again. So this was the Fermi gamma ray detector. It saw it 2 minutes after the gravitational wave, event arrived, Fermi also has a trigger warning that alerts other telescopes when it sees a gamma ray event for follow-up. And so even though these guys took 27 minutes, Fermi had already alerted it. And gamma rays also are not very good at localizing things, but because it had alerted a number of other telescopes, they started seeing the thing in the optical and the infrared. Okay, so there were 2 telescopes that were actually triggering the same event. It took a while. Sorry, this is an artist's representation of the physics that we think were involved. You first have the gravitational wave phase. You then get very close, you merge. Then you have a lot of thermonuclear activity. You have your gamma ray burst going out first. You have a disk forming, which typically gives you infrared or X-ray. That's a gamma ray burst that Fermi picked up. Okay. So I'm going to show you some of the other observations. So this was made by, that was made by NASA. I'll discuss the things, and then I'll go back to that simulation that you can actually see sort of how our observations have sort of correlate with a story, and it is a story that they give us. It's a whole bunch of cobbled together physics that people have seen from different fields, and people are still, for the first time actually, they now have the full picture of where it comes from. That event, they call a kilonova. It was predicted 30 years ago, okay? 3 years ago, or 3 or 4 years ago, there was a claimed detection of a kilonova, but nobody was sure. They couldn't get the light curve well enough to actually see the, to confirm that it was a kilonova, but there was a huge slew of papers about it anyway. This is the first 100% sure kilonova that they've seen, and there were surprises. Okay, so here is the location in the UV. Here's the event in the infrared. Here's the event in the radio. That, I think, is the X-rays. I'm not sure, right? But it was actually, it statistically can be seen there, right? The gravitational waves doesn't give a great sky localization. Fermi also doesn't give a great sky localization. But these other instruments, without a doubt, are all the same event. You can statistically show that it's the same location and that it correlates with the gravitational wave event. So some of the information that's been collected from the whole batch of papers that you've seen is within 12 hours after the event, the community was reasonably sure, with all the various observations, that it was localized to galaxy NGC 4993. And you see the Hubble image below, and what it basically shows you is how it's fading. Okay, there's a certain light curve that was predicted to be associated with these kilonova, and it's close to that. It's basically a stellar flare in the light waves that results from the collision, and then it's a first observational proof conclusive. I mean, they've been conjectured once prior, but this is the first observational proof. It's also the first observational proof of an electromagnetic source for a gravitational wave, which also stopped all discussion whether the gravitational wave was actually a real astrophysical event. It was seen by dozens of observatories, as Ad said. It's in the constellation Hydra, so the light has traveled 130 million light years from Earth. So this is looking back into far history. It's interesting that the gamma ray, so the prediction is that gravitational waves travel at the speed of light, as does electromagnetic radiation, and this is a great way to verify it, right, because the gamma rays arrive 2 minutes afterwards, and that's to be expected because the emission mechanism for the gamma rays has to be that shock front that goes forward, so it takes 2 minutes to actually do that. If the waves were not traveling at the same speed of light over this distance, you would have seen a huge dispersion, okay, much more than 2 minutes. So it confirms the speed of the gravitational wave compared to the gamma rays. What they also could do, they could use Hubble to get spectroscopic data of the ejector, so you can establish the speed with which it was moving, and some of that ejector was moving at a fifth the speed of light, which is once again, it's to be expected, right? That's seen from simulations of neutron stars as well. It's a tremendously powerful event. In fact, if you go back to that fact sheet, you can see the amount of mass. It's a fraction of a solar mass that's lost, that's simply vaporized into gravitational waves. These events are tremendously, sort of ditched a tremendous amount of power into our universe. The infrared that they saw with Hubble and Spitzer results from the decay of radioactive neutron star-rich elements. It's the R process, and it's basically a major source of platinum and gold. That's why I said it was a gold mine, both physically and with respect to what we learned from it. What was unexpected is Swift made a UV detection. And typically this, in other systems, represents a disk, okay? What was not expected, and it's unexpected because the neutron star simulations we had very often did not form disks in the merger event, so there must have been some other source for the disk. And that people are still speculating about, but yeah, okay. And then the other thing was Chandra and the X-rays saw the X-rays only 9 days later. And this was also unexpected because if you have this huge gamma ray thrust, you tend to associate that with a jet, and you tend to associate the X-rays with a jet. And what people conjectured was that the jet was not actually, the viewing angle was wrong, that we were not looking straight on at the jet, that we'd seen the gamma rays simply because the gamma rays has this huge sky angle when it actually makes the shock wave, whereas the actual jet was at an angle to our field of view, and only after 9 days did something happen or rotate or it expand big enough for us to actually see it. Okay, so from this we can learn some of the morphology of the actual event, and this is a continuing thing. I mean, the radio afterglow happens months afterwards. So when this thing goes off, a number of people said, "You're looking at an SKA." I'm like, I have nothing to do with the SKA, but you can relax. It's going to you've got a month to get this thing going. But it was observed with the SKA. It was observed with SALT too. So South Africa was pretty much featured in doing the follow-up. Okay, so here we have the gravitational wave in spiral. You have the merger event that triggers the jet that sends out the gamma ray burst as well as the X-rays. There it goes. Okay, then you have that disk forming, which was unanticipated. And all the while you have this tremendous nuclear energy and the R process going that makes all the other elements, or heavy elements, that we are so fortunate to have in South Africa. Okay, so in conclusion, we live in a very different world to what we lived 3 years ago. We know definitely there's this underwriting sea of gravitational waves that lives below our detection level. We've seen a few of them. I wonder what Einstein would do if he was alive now, because he didn't like quantum mechanics, right? He didn't like its unpredictability, but intrinsically, because on the very basic level, our ideas of measurements are now have this perturbation on them that are formed by massive things colliding. His own theory of relativity actually introduces unpredictability, and we're starting to understand the relationship between the two for the first time. The big thing is when we get to test general relativity, when we actually get sort of more accurate measurements, when we go beyond just measuring the mass and the spin. LIGO might not be the optimal instrument for that. There are instruments that can do that coming. LISA, detecting a very good pulsar binary system with the SKA that's got a very close orbit, could also do it. It's easier to do the mathematics for testing if you have something like that, closer than the best ones we know. So yeah, I mean, and then there's also looking for gravitational waves that have a much longer frequency or wavelength. That can also be done with pulsars, where you use them as buoys in the space-time to sort of pick up perturbations. Once again, for the southern hemisphere, the SKA is, or Meerkat in particular, is the instrument of choice. I mean, at the moment, the people that do this is the International Pulsar Timing Array. The Meerkat data would play a very important role in it, and how that's incorporated is being discussed. So for the youth in the audience, I mean, Meerkat's a good thing. There's a tremendously bright future in having these instruments and being able to play with them and being able to compete on equal level with the best observatories there are in the world. So thank you very much.
Question.
Yeah, questions.
Please, ladies and gentlemen, are there any questions for Jeandrew? Could you...
Which sound? Oh, that one I like. So, that's the best part. That means you got the optical. Oh, sorry, the gamma ray or the EM spectrum. That chip is indicative of relativity and many other theories actually as well. And it remains, the initial structure remains the same whether you're colliding neutron stars or black holes.
When you show those signals as a wave, that the amplitude that it measures, or that metric, or that value, or the thing that's actually being measured, what is it? I mean, I guess eventually it's something like voltage, but what is it actually that you are measuring there?
So you mean that?
That wave, the amplitude of the wave, basically.
Okay, that's the gravitational wave strain.
Strain.
Yeah, it's basically, and how we measure it is we use the lasers to measure the displacement of the actual test masses. Right, so you have your, I don't know how far back I can go. You basically have your hung test masses, then you set it up as an interferometer, and we're physically measuring this, well, it's the displacement that we convert into a strain measurement and that's the amplitude that we measure. We call it the waveform. You can either measure the strain or you can physically measure the displacement. There's a conversion factor between the two.
How much is the displacement?
It's, well, the typical thing is like 10 to the minus, a fraction of the width of the hydrogen atom, 10 to the minus 16, 10 to the minus. It's tremendously small.
And so their displacement is because the space-time is being warped?
Yes. Yeah. So you basically, as your gravitational, so I didn't explain that well at the beginning, I'm sorry. So as your gravitational wave, it's a quadruple form of radiation, right? So what it does, suppose you have, okay, so take a step back. If you have electromagnetic radiation and you have an antenna, right, the charges move sympathetically to the wave that comes past, it's just dipole radiation. Gravitational radiation is a quadrupole radiation because the sources are not charged. And what it does to a series of test masses, it basically squashes it in the one way and lets it expand in the other way. And so what happens to those arms, and that's the design of the detector, they basically scrunch in the one way and expand the other way and changes the path length of light between them. And that you can measure very accurately using the interferometer.
In Monty Python, it has the Meaning of Life movie clip about the miracle of birth and the machine that goes ping. Did that have anything to go with?
I have no idea. But I definitely know there's a basic appeal.
Is there a little bit of miracle of birth, maybe?
I actually don't know who made that simulation, but it definitely sort of, yeah, I mean, a field is born. It literally is. So yeah, thanks for that.
I just wanted to know whether there's a theoretical prediction for a neutron star and a black hole colliding.
Yes, there is. In fact, it sits roughly between the... okay, let me take a step back. We've never seen a neutron star black hole pair in any way observed. It's one of the holy grails that LIGO goes for, as well as the pulsar timing group. Having said that, there's very little, if you look at this formation mechanism, that formation mechanism, right, there is a stage if this, in the event that the secondary star has a mass lower than, say, 3 solar masses or so, then it won't collapse into a black hole, it'll collapse into a neutron star. So that's a formation mechanism for a black hole neutron star method. And when they were working out the event rates for LIGO, they did a lot of or various initial configurations, what do you form? And there's a significant fraction that do form, or not a significant fraction, that do form black hole neutron star binaries. So they anticipated, we just haven't seen them. Exactly what the fraction is, I can't remember, people have worked it out. So no, it's not as if it's an unlikely event. It's, I mean, just following the same argument for this formation, the system for the two black holes. Yeah, you can imagine a black hole neutron star will form as well. But I'm not an expert in that field. I just know it's been done.
Just a quick one out of interest, especially while you have that slide there. We have a big, I don't know whether we call it black hole or what. One is big, one is small, okay? So in the event that occurred, the size of the black holes that collided, were they of the same size or not? If they were not, which one was moving closer to the other one at a faster rate, if they were not of the same size, more or less?
Okay, that's a good question. So the black holes that we have measured are roughly the same size so far. I mean, here the sizes of the circle is an indication of their masses. Okay? Now, and the two neutron stars that collided were also roughly of one solar masses. Part of that is due to the way we've chosen due to the way that the measurements are made. The waveforms are not very sensitive to the mass ratio. So if there's a bias, it tends to bias towards equal mass objects. So in that case, it's not really important, right, because there's a symmetry. But now to answer your question, which I think is more about, suppose you have an extreme case, right, where you have a reasonably large object, massive object, and then a smaller one. If you do classical mechanics, there's a thing called the center of mass between the two objects. And the way you do the mathematics is you can actually decouple the equations around in your center of mass frame. So it tends to be like closer to the massive black hole. There's a point at which you can decouple the equations. So it's basically the black hole stands, it's like the sun and the earth. Okay, that's a good example. Right, the center of mass of the sun and the earth sits somewhere within the sun. So it looks to us as though the earth is rotating around the sun, but that's not true. Actually, the earth's rotating around that point, and the sun is also doing a little wobble around that point. And the same thing exactly happens in general relativity. It's harder to calculate, but the idea of a center of mass also exists, roughly. I don't know if we shouldn't have wine, or do you? Because the pulsar timing will take me 5 minutes, and I think people are weary.
Ladies and gentlemen, I think you'll agree that that was absolutely awesome. Thank you very much indeed, Jeandrew. Baie dankie.
Vreeslik dankie.